Okay, so welcome to Focus Private Tuition. So we'll proceed with our topic of equilibria, and I hope by now you must be able to identify a conjugate acid and a conjugate base. You must be able to identify a suitable indicator for a suitable acid base titration. We saw the different combinations. I hope you explored that further. So in this particular video series, we're going to be looking at how you can calculate your pH. We're going to look at the acid dissociation constant. We're going to look at solubility. We'll go very far in this series, so hang on and let's talk here about the pH equation. So how do you calculate pH? So pH is a logarithmic scale that measures the concentration of H plus ions. Remember, when you're dealing with logs, you're dealing with powers. So that's a general interpretation of 0 very acidic, 7 means neutral, and 14 very basic here. Okay, so this is the pH equation. pH is equal to negative log base 10 concentration of H plus ions. So we need to know the concentration of H plus ions for us to be able to calculate pH. Okay, so for example, calculate the pH of 0.03 moles per cubic decimeter of HCl. The first point to note is that hydrochloric acid is a strong acid, and we assume it dissociates fully. Remember what I said in the previous videos. This means that the concentration of H plus is equal to the concentration of HCl. So these are equal in concentrations because we're saying exactly the number of moles of HCl that dissociate will give us the exact number of H plus ions. Okay, so we're going to take 0.03 and substitute into this equation, and if you place that into your calculator, realize that the pH is 1.52. The concentration of hydrogen ions can also be calculated when we know the pH, so you can do the reverse. If you know the pH, you can know the concentration of H plus ions. So for example, here calculate the concentration of hydrogen ions of nitric acid with a pH of 1.7. so what you have to do is you have to go to this function on your calculator, and you can calculate the concentration of H plus here as equal to the to 10 raised to the power of negative pH, so negative 1.7 for our pH there, and we can calculate this using our calculators as 0.020 moles per cubic decimeter. So should be able to play around with this pH equation. So okay, acids, it's important to know that we have polyprotic acids. So this acid here that can donate 1 mole of H plus ions per every mole of the acid is called monoprotic. In other words, it produces 1 mole of H plus ions. But if you look at sulfuric acid, it is 2 moles per every mole of sulfuric acid. Therefore, it's called diprotic. And we have other acids such as phosphoric acid, which is triprotic, or you can say polyprotic at this stage. So it's important for you to know that the number of moles of H plus ions that are donated by each acid are also different. This is important when you now want to calculate the pH given the concentration. So in the previous example here, the acid was monoprotic. So this is why we said 0.03 is equal to exactly 0.03 moles of the acid, which fully dissociates, would dissociate to give you 0.03 moles of H plus ions. So if it were a sulfuric acid, would get double that, which would be 0.06 moles. So you should be able to understand that it's because of these things here. Polyprotic acids such as H3PO will give you more moles of your H plus ions. So you need to remember this when you are calculating the manipulating your stoichiometry. Okay, let's proceed. So let's talk about calculating the pH of strong acids, which you just did. So when calculating the pH of strong acid, make sure you assume they dissociate fully. So we made that assumption for the HCl. So this is what we always do. And now I wanted to say proticity of the acid. Okay, so monoprotic acids here, like HCl, will give you 1 mole. 1 mole of the acid will give you exactly 1 mole of H plus ions. Okay, so the concentration of the acid will be equal to the concentration of H plus ions, given that it's monoprotic and it's also a strong acid. Okay, all right. So for example, the pH of 0.5 moles per cubic decimeter of HCl, again, we are going to assume 0.25 moles per cubic decimeter of the H plus ions, and we can calculate our pH as 0.6 here. Okay, diprotic acids. Now, the stoichiometry comes into play here. Diprotic acids dissociate to produce 2 H plus ions for every acid molecule, so it's going to be double. So if you have 0.25 moles per cubic decimeter of sulfuric acid, the concentration of H plus are going to be 2 times the concentration of the acid. So 0.25 here times 2, we get 0.5, and our pH is going to be 0.3. You can tell here that diprotic acids here are stronger acids. If you check the pH here, this one is less than this one. So 0.3 versus 0.6, you can tell that your sulfuric acid is going to have is going to be more acidic given the same concentration as your HCl. Why? Because it's diprotic and hence a more stronger acid. Okay, let's talk about calculating the pH of strong bases. So similar to strong acids, when calculating the pH of a strong base, we assume that they dissociate fully. For example, sodium hydroxide will dissociate fully, and you can see here we are not even putting the reversible sign because the reaction is going to be primarily going to your right because these bases dissociate fully. Okay, strong bases, for you to be able to calculate their pH, you need to make use of this which is called the ionic product of water, Kw. So to calculate the pH of the base, you need the concentration of H plus ions. To get this, we need to use the expression of ionic product of water. Okay, so to work out H plus, we need to know Kw and OH at a specific temperature. Once we know H plus, we can work out the pH. So let's look at an example so that you get this. Okay, example, calculate the pH of 0.15 moles per cubic decimeter of sodium hydroxide solution at, you are given here the temperature, and you're also given the ionic product of water at that temperature, which is 1.4 times 10 to the power negative 14. Okay, so first substitute the figures into the Kw expression. So 0.15 is going to be the concentration of the OH minus ions. Remember this, for every mole here of the sodium hydroxide that dissociate, will get exactly 1 mole of the OH minus ion. So we're going to get 0.15 moles of the OH minus, and we substitute, and we know our Kw value here, and we can rearrange it to calculate H. So once we know our H, which is equal to, in this case, 6.67 times 10 to the power minus 14, we can now take this and put into our equation for pH. So third, calculate the pH. pH is equal to negative log concentration of H, which is 6.67. So we'll get a pH of 13.18. So you make use of this equation, the ionic product of water, and remember that you will always be given the value of Kw at a specific temperature. So you must be able to manipulate this one. Okay, so let's talk about the acid dissociation constant quickly. Remember, it's under equilibria, and an equilibrium is established every time you have an acid-base reaction. Except of course for those strong acids and strong bases that we looked at. So weak acids only dissociate slightly in aqueous solutions, so we have to use another constant to help us work out their pH values. So here we can assume that the concentration of H plus is equal to the concentration of acid for strong acids, but we can't do this for weak acids because they do not fully dissociate. So this is no longer a valid assumption for the weak acids. Okay, so the assumption number 1 here, only a small amount of the weak acid dissociates, so we can assume that the concentration of the acid at equilibrium is almost equal to the concentration at the beginning. So basically nothing has changed in terms of the concentration of the acid, because these weak acids do not fully dissociate. Only a small proportion of the acid molecules will dissociate. Hence, we have roughly the same amount of concentration as we had at the start. So this is the assumption that you need to know about. Okay, the equilibrium law can be applied here as we have an equilibrium reaction, so we can use Ka expression to represent a reaction. So for an acid HA that dissociates to form H plus, and A minus, we can write our Ka expression. Remember what we did for Kc earlier on when we were saying products over reactants. So we can do the same. Concentration of H plus raised to the power of 1, A minus raised to the power of 1 divided by HA. Okay, but take note here, this assumption now is we are saying the concentration of the acid at start, because we said here the concentration of the acid at equilibrium is roughly equal to the concentration of the acid at start. Why? Because only a small insignificant amount is dissociated. Okay, so assumption number 2 is that the dissociation of acid is greater than the dissociation of water present in solution. So we can assume that all the H plus ions come from the acid. Okay, the dissociation of the acid is greater than the dissociation of water. So there's water itself can dissociate to form OH minus and H plus, but we're saying the dissociation of this acid, even though it's weak, the dissociation is greater than that of water. So all the H plus ions are coming from what? From the acid. So H plus, H plus here, concentration of H plus ions are equal to the concentration of the A minus ions in aqueous solution. Okay, so remember these two assumptions are valid here. So let's now simplify our Ka expression now that we know this. So we can say here Ka is equal to the concentration of H plus ions squared, because we're saying here the concentration of this conjugate base, right, is equal to the concentration of H plus ions. Remember, for every mole of HA we get exactly 1 mole of A and exactly 1 mole of H plus. So we can express our Ka in terms of H plus only, in which case it becomes concentration of H plus squared over the concentration of the acid at the beginning. So let's make use of this these expressions in calculation. So calculate the pH of 0.03 moles per cubic decimeter of ethanoic acid, which is a weak acid, at 298 kelvins. The Ka for ethanoic acid at 298 is 1.76 times 10 to the power -5. So here you're already given your Ka value, so all you have to do is create an expression for Ka. So write down the expression. Say it's going to be concentration of H plus ion squared divided by the concentration of the acid at start. So rearrange for H plus and remove the square sign there, and we are going to have our H squared being equal to 5.28 here. When we remove the sign, when we apply our square root sign here, we're going to have 7.27 times 10 to the power -4. So you can calculate the concentration of H plus given your Ka value. Okay, you must be able to create this Ka value and understand assumptions. Okay, calculate the pH. So what you simply have to do here is now put into your pH equation negative log base of H plus ions, and you get the pH of 3.14. Okay, all right. Calculating the Ka, or concentration of the weak acid, we use Ka expression to calculate Ka or concentration of the weak acid. Let's look at this. So calculate the concentration of methanoic acid at 298 kelvins. The pH is this 3.14, and the Ka for methanoic acid is 298 is 1.77 times 10 to the power -4. So here the question is calculate the concentration in moles per cubic decimeter. So how do we go about this? Firstly, calculate the H plus ions using the pH equation. So pH is equal to this. Remember what we said here, concentration of H plus is equal to negative log pH. So negative log our pH is 3.14, and we have a concentration of 7.24. Now remember this expression here, it can help you to calculate the concentration at start. So we are given the Ka value, which is 1.77. So we're going to substitute into that 1.77 times 10 to the power -4, and we now have our concentration of the acid of the H plus ions. So we'll substitute those, and we can calculate our concentration at start, which was 2.96 times 10 to the power -3 moles per cubic decimeter. So these manipulations, you must teach yourself how to rearrange these different formulas and manipulate them depending on what you're given. Okay, Let's see what else we have. Calculating Ka is just 2 steps. Okay. We'll just talk about any product of water, though we've talked about it, and see how it can be manipulated. So you need to remember that water exists in equilibrium with these ions. In other words, a glass of water doesn't just contain H2 or molecules, it contains these ions as well, your H plus and your OH minus ions. Okay, so this equation can be simplified to this one, and according to KC, we were supposed to have this, but the equilibrium law. But here we need to remember that what we said, that here water dissociates into its ions very weakly. In fact, there is solid OH minus and H plus ions compared with water molecules. So we assume that the concentration of water is a constant value. Okay, so if we multiply the two constants KC and H2O, we get a new KW, which so the units, you need to know the units here: moles raised to the power of 2, dm raised to the power of -6 here. So we are saying here that the KW expression is going to be like this. So what you need to take home is that this one is considered a constant. Okay, it's considered a constant, so it's not going to appear in your, remember what we said for KC, for heterogeneous systems where you have a solid, we said a solid, the concentration of solids does not appear here, or the concentration of pure liquids, if you still remember that. So same thing here, because these are assumed to be constant, so we remove our H2O here and we're left with this. Okay, so I think we should end here for now, and then we'll talk about we want to move to, we'll talk about pKa, and we'll also talk about buffers. We'll talk about KSP in the coming lessons, so hang in and tell someone to join us in our online lessons on the numbers that are provided. So I'll meet you in the next lesson. Enjoy your studies.